So problem 4, chapter 4, 39 is the question. Now in order to write the mesh equations, in order to use the mesh current method, we've got, so how many meshes here? We've got 3 meshes, easy to see. And we've got to choose mesh direction for each, so I will be choosing it like that. So this is, let's say, first mesh, and that is second mesh, and that is third mesh. Element current references I have chosen like that. For this, like this, and this for this. So according to passive sign convention, this reference is going to be like that. For this one, it's going to be like that as well. So for this one, we already know. So what we've got here, we've got voltage controlled voltage source. So it is a good choice, isn't it? Because I am going to write for mesh currents, I'm going to write KVL equations. KVL, Kirchhoff voltage law equations. While writing the voltage law equations, I'm going to write the voltage of this element in the definition relation of this element. I can use the definition relation while I am writing Kirchhoff voltage law equation. So I can write it for this definition relation, for this element definition relation. Voltage of voltage controlled voltage source is equal to 65 V delta. V delta is already given here. So that's the definition relation. While I am writing the Kirchhoff voltage law equations, I'm going to meet that, and I can replace this with the definition relation. So that means I'm not going to write additional supplementary equation because of this dependent source. These are independent voltage sources. Since I am writing the Kirchhoff voltage law equations, I can use the definition relation of these independent sources, which are 125 volts. So there would be no solution, no problem, because I am writing the Kirchhoff voltage law equation. No supplementary equation is going to come from those independent sources as well. So that's why we have chosen the mesh current method. So let's 3 equations I am going to write, and I am not going to do it step by step. I am going to directly write it. I'm going to write the mesh current equations directly, but I know in my mind that KVL equations that I am going to write. For this one, the voltage is 2.65. So I am using the definition relation directly. The voltage of this element equal to this, isn't it? So V delta is this. V delta is this resistor current, the resistor voltage. Resistor voltage, if I use the definition relation, multiplied 100, resistance value, multiply this current, E 100, let's say. This is V delta. So this current, so I'm going to go directly, I am writing as I said, this I0 current, I100 current is this element current. In terms of mesh current, it's going to be IC2 minus IC3. So this same direction, IC2, and this is opposite direction, this is minus IC3. What I wrote this element voltage, and I used the definition relation, and I transferred this to mesh currents. So that's this voltage. What about this voltage? Minus voltage of this. Voltage of this 25 ohm resistors is 25 times this IC3 direction is the same, so IC3 minus IC1. IC1 go opposite direction, isn't it? This and this opposite direction. So minus IC1. And the last one here is the voltage of this. So mesh current direction is opposite, so minus sign I put in first. And then I'm going to write the voltage of this. Voltage of this resistor is 15 times current. Current is IC2, same direction, minus IC1, opposite direction. IC2 minus IC1 is equal to 0. For this one, now this is going to be now positive sign, so I'm going to repeat this one, plus 15 times IC2 minus IC1. That's this voltage. This voltage that I already know in 100 plus it's going to be, because direction is the same, 100 times this element current, which is IC2 IC3. I am not considered once again because in here I wrote this element current. I just repeated here. And this same direction, so it is going to be same direction plus sign. Voltage of this is 25 times IC2. There is no, there's just one mesh current related with this element, and directions are the same. So it's going to be IC2 is equal to 0. So for this one, so same direction 25 times, not equal to 0, so I made a mistake, sorry, make it correct. So in this loop, I've got this Vs, and direction is the opposite. If I write the voltage on the left-hand side, I'm going to write minus 125, because I am writing Kirchhoff voltage law equations. This is independent voltage source voltage, isn't it? So this minus 125, I put it on the right-hand side, 125. So for this one now, the voltage of this here, already here, but this time the directions, both of them, mesh current direction and this element current direction is the same. That's why it's going to be plus 25 multiplied voltage of this 20 multiplied with this current in terms of mesh current. This is I32 IC2 minus IC1, IC3 minus IC1, which is the same, isn't it? So that is going to be same direction, not like this. This mesh current direction is the same as, oh, just a moment. That's good news because I can correct myself. I made a mistake. Now, I said the direction is downwards here. It is not downwards, isn't it? Because according to passive sign convention, it's going to be this direction. So when you write it here on the left hand side, it is going to be positive. If you move it to the right hand side, it's going to be minus. I correct myself. Similarly, this reference, once again, according to passive sign convention, the current reference must be upwards. So it's going to be minus 125. Anyway, so 25, so I put this, that's going to be minus direction, the opposite direction, left hand side minus, right hand side, it's going to be plus, isn't it? In here, both of them direction are the same, put it right hand side minus. In here, left hand side it is minus because it is opposite. Right hand side it's going to be positive, isn't it? So I wrote this element voltage and this element voltage. What about this element voltage? Is 85 times. There's one mesh current here, same direction. It's going to be IC2. And this minus this 100 ohm resistor voltage. So this is minus of this, isn't it? 100 EC2 minus EC3. So I've got three equations, three unknowns. How you're going to calculate it? So write all this when you open it. So I already done it, so I'm not going to repeat it here to save time. It's going to be, so if you, this one is going to be 4IC1 plus 25IC2 minus 29IC3 is equal to 0. The second one, minus 5EC1 minus 20EC2 plus 42C3 is equal minus 25. And this one, minus 3IC1 plus 30IC2 plus minus 20IC3 is equal 25. So three equations, three unknowns. How you can solve it? For example, you can eliminate IC2. If you multiply this one with 3 and with 2, that's going to be disappear. Write an equation between IC1 and IC2. IC3, so you can find IC1 in terms of IC3 and put it in this equation. If you do all this calculation, IC1 is going to be 7 amp. IC2 is equal 1.2 amp, and IC3 is going to be 2 amp. So once you found this, these are the mesh currents. From this mesh currents, what you're going to do, you can find all the elements currents. For example, this IC2 is, this current is the same, isn't it? 25 ohm resistor current is equal to IC2. This 85 ohm resistor current is IC3, 2 amp. And this element current is IC1 is 7 amp. This element current is IC2 minus IC1. Since you know this, you can find this. So you can find all the currents. Once you find all the currents, you can find all the voltages. These voltages are known. So what about this voltage? So you know this resistance current is IC2 minus IC3, since these are known. So this element current is known. This element voltage is multiplied 100, you get the voltage. If you multiply this voltage with 2.65, you get the voltage of each element. So once you've got these three currents, you can find all the elements current and voltages. One thing that I would like to remind you is this, you see, since you've got two independent sources here, you could prove or validate that superposition theorem is true. So in here, you're going to deactivate this, that means short circuit here, and you're going to find this circuit solution. And then you're going to deactivate this one, and put that one in. You're going to find this circuit solution. If you add those two solutions, you're going to find the solution that we found here. So manually, this is what we have done it, and I'm going to put in the Proteus solution of this circuit as well in the Proteus section of these examples, so you can follow that there. So that is the end of this video then.